Is everyone ready? So Prof. Gu is not here, as everyone might remember, so I'm going to be doing the lecture for today as a substitute. Hopefully we will not go 3 hours. I just have this material to get through, and then once we're done with this, we'll call it night if that's okay with everyone. Unsure how long this will take, but I'll try to cap it for sure at 2 hours, hopefully an hour and 30, if that's okay with everyone. Yeah, so I had the option we were talking about, Prof. Gu mentioned sort of briefly last time, which is Lagrange duality and optimization. So the idea of Lagrange duality is you can take an optimization problem. Oh, and I have notes, by the way, that I'll send out. If you want to do it, that's totally fine. But you can also just, I'm going to put that on the website. But okay. But you can do whatever you want. I'm just saying, if you want to type them up, that's fine too. So Lagrange duality is all about taking optimization problems that may be super hard. For example, they could be NP hard to solve in general, and you can go through a process to convert that into an intimately related optimization problem called the dual problem, which is, again, intimately related syntactically, but also can give you information about the other problems. For example, we're going to see later today an optimization problem that is, I'm pretty sure it's NP hard to solve in general, but by passing to the dual problem, you get to an efficiently solvable program that gives you a lower bound on this problem, for example. So that's something that might be interesting in general, but also it's just, it gives you computational tools for dealing with these problems, and it's also intimately related to the linear algebra behind all of this. Although I'm not going to get into a lot of details about doing these things in banana spaces or anything like that, we're going to stick with Euclidean space for the lecture. The other thing I could have talked about, which I'm not going to talk about, is kernel methods. There's some slides on the website right now if you want to look at those that you can look at. Gu mentioned those last lecture, but I basically chose between the two, and I know this stuff better, so that's what we're going to do for now. Who here has seen some sort of Lagrange duality before? Phrased as that. Okay, like maybe 3, 4 people? Okay. Who here has heard of like a Lagrange multiplier? Probably everyone. Yeah, from multivariate calc. It's the same stuff. It's just a little bit more in detail, but it's at the end of the day, it's the same material basically. But this stuff is going to be much more applicable and framed much more broadly. Yeah, so again, I'm basically going to start out by defining what a generic optimization problem is and sort of some common notation that we're going to use. And then I'm going to talk about how to convert those optimization problems into what's known as the dual problem, and show how that's related to the original primal problem, is what it's called. And then I'm going to talk about what's known as strong duality. So I mentioned before how dual problems give you lower bounds to the primal problem if you solve them exactly or inexactly. And what we're going to look at, I'm not going to prove this, but the book that I'll reference in a second has the proof if you want to look into it. I'm going to show some conditions that are pretty easy to check about problems that guarantee that you have strong duality, namely that a lower bound you get from passing to the dual is tight. So that might be of interest to people. Then we're going to go through a couple examples. So what's the dual of a linear program? What's the dual of that NP hard program I talked about before that turns into a semi-definite program in the dual space? And then also I'm going to talk about an application to how you can use duality theory to exactly solve linearly constrained quadratic programs, which are sort of convex problems, but you can actually solve them in one linear system solve if you look at the dual in conjunction with the primal problem. And then finally, I'll talk about some small open problem that I thought about this weekend that came up in a different class of mine. It's about numeric linear algebra, but it is related intimately to the convex optimization tasks here. So I'll talk about that. But yeah, and does anyone have any questions or anything about anything in Prof. Gu not being here or anything like that before we start? Nope? All right, so I'll, again, start. First we're going to talk about what a generic optimization problem is. So again, you might have seen optimization problems framed in classes, like for example, an algorithm or something like that. You could be talking about finding like some sort of bipartite matching of a graph that satisfies some sort of property, maximality, something. But it turns out that any sort of thing you can frame as a maximum of a function over a set, namely you're taking some objective you want to maximize, and then you want to constrain the sort of space that your solutions can live in. You can frame it in this special form that's quite general but looks kind of clean to deal with, and so we're going to do that. And so a generic optimization problem, and for us at least, is going to be something of the form minimize a function f naught of a vector x. So this is a vector x that's in Rn. And can everyone read that everywhere? We're good? So yeah, so we're going to be minimizing a function f naught of x. It could be non-prime of x, it could be whatever to start out with, subject to some constraints. We're going to have inequality constraints and equality constraints. So for example, we're going to have the fi of x being less than or equal to 0. These are your inequality constraints for I equals 1 all the way up to m. And then we're going to have some equality constraints, hi of x equals 0 for all I equals 1 up to p. Okay? So this might look very specific, but because these functions here are generic, it turns out that this encompasses pretty much, I don't think you could think of some optimization problem that you would not be able to frame in this form. As an example of that, we'll show how to convert just a generic integer program into this form. Has anyone here heard of the word integer programming before? Anyone? So it's like the canonical NP-hard problem, basically, in some sense. And so, let me erase some of this. So again, as I just said, we've talked about a little bit about linear programs in this class. Namely, a linear program is when you want to optimize, or let me phrase it this way. So a linear program is when you have a polytope, so like a polygon that you would think about in grade school, but in multiple dimensions. So you have a polytope, and a linear program asks, given some direction in sort of Rn, which point in that polytope is most in that certain direction, right? And so an integer program asks the exact same question, but we add the constraint that your points that you're considering that you want to optimize over have to be integers, like in terms of their coordinates, as well as fitting in the polytope. And so the integer program can be formalized in multiple ways in terms of how you write them down, but for our cases, you can write all integer programs in this form as maximizing some function C transpose is a vector, C transpose x, subject to some constraints, namely ax less than or equal to b, element-wise. So ax is going to be a vector, and this is saying that basically, if you look at the rows of A as AI, you're going to say that AI transpose x is less than or equal to b, namely that the component of a vector x in some certain direction is bounded by bi here. So that's what you want to think of this as. And then also that x has integer components. Okay, so can anyone think of a way to quickly formalize this program in terms of this form? Anyone? Can anyone move any of these things into more of this form? So I think the integer constraint is probably the hardest bit here, but were you going to say something?
Oh, just take a negative in the top one.
Exactly, great. So maximizing a function is the same as minimizing the negative of the function, right, in terms of the value you find. And so this is the same as minimizing negative C transpose x, all right? I already sort of gave a hint about how you could frame this sort of vector inequality constraint in terms of individual inequalities by 0. Does anyone have an idea about how to convert that ax less than or equal to b into this form here? Anyone?
Subtract b.
Sure. How would we do that component-wise? So that it's like exactly in this form?
I guess it'd be the inner product of the column, the vector.
Yeah, so as I sort of suggested, this constraint, which is what you just said, is the same as ax minus b being less than or equal to 0. Can we all agree on that? Everyone's good? Okay, so it turns out that every element of this vector is of what form? Can someone else say what each element, so like ax minus b I. What does that look like? Anyone?
Well, I mean, I guess it's I for a divided with x.
Yeah, so we can write this same thing as, I'll write that as like little ai, right, for the ith row, transpose x minus bi less or equal to 0. Okay, so now we have most of this integer program in the form here. Can anyone think of a way to sort of do maybe the hardest part of this? Yeah?
X minus 4x.
Oh yeah, that's a good one. So that's not exactly what I was thinking, but that's a good one. You could say xi, each component, xi minus the floor of xi equals 0. And that's going to be sort of like piecewise linear, but not continuous in general, right? Can anyone think of a way to do this that might be continuous, just for the sake of thinking about it? Yeah, so that was the one I came up with originally, but these both work, right? So another way, so again, we can replace the integer constraint with this constraint, or we could say that the sign of pi xi equals 0, right? And so, I mean, if you look at this, if you ignored this, this would just be a linear program that's super easy to solve. Your computer can do it in like end of the 1.5 time or something nowadays. As soon as you add this, it turns into an NPR problem. And sort of, I guess you can look at this and be like, oh, well, clearly that's kind of hard to deal with, that like sign of whatever. You constrain yourself to the roots of this weird function. But yeah, so I guess the point here is that this is some problem that we just came across in the wild, and we can convert them into this form. Take my word for it, or maybe you can convince yourself that pretty much every optimization problem you care about can be formed in this way by basically doing the exact same steps that we just did. Okay? So now we're going to talk about the dual problem. So there's a couple different types of dual problems, but this is the one that's most heavily used. There's like Fenchel, I think, duals and things like that, but this is going to be the Lagrange dual formalism in optimization. And so what we're going to do is take this problem right here that I'm going to denote the primal problem. And so this is called a mathematical program because you're sort of telling this, what ends up being a computer, but you're telling someone to solve this in math. And so I'm going to call the optimal value of this P star for primal optimal value. And what we're going to find is another sort of problem called D star that's going to tell us sort of things about D star, basically. But it can be a different problem. And so to begin with, we're going to want to have some heavy machinery that's from convex analysis, but it's actually quite simple. It sort of feels a little tautological, but it's going to be very helpful. So I'm going to define sort of most of you have probably seen like indicator functions of sets that sort of 1 if you're in the set or satisfying some constraint, and 0 otherwise. This is going to be the convex analysis version of that indicator. And so instead of having 0 or 1, you're going to be 0 if you're in the set, and infinity if you're not in the set. So convex analysis, people usually add infinity to your real numbers, and just take my word for it that works for everything we're going to do. Again, so right now, what I'm going to want to do to create the dual problem is change this problem that's constrained into an unconstrained problem that might be super nonlinear or non-continuous. Okay? So in particular, this problem right here is going to change exactly to minimizing over x f naught of x. So again, this is exact. F naught of x plus a sum of over our constraints equals 1 to m of this indicator function. So less than or equal to 0 of fi of x plus the sum from I equals 1 to p of the indicator function at 0 exactly of hi of x. Okay, so what does this mean? Basically, the indicator function less than or equal to here is going to be infinity if you're in the positive numbers and 0 otherwise. Namely, if x does not satisfy the constraint fi of x less than or equal to 0, this bumps the objective function here to infinity, and as a result, that no minimum could ever possibly satisfy that of this function, right? But on the other hand, if x satisfies the constraint, this doesn't contribute to the function at all, right? And so if you're in the constraint set here, if all the constraints are satisfied, this reduces exactly to your original problem. But if you don't satisfy any constraints, then your objective function goes to infinity, okay? Does everyone get the intuition here? Yeah? Okay. So, again, let's articulate here. It's going to be equal to 0 if x is non-positive and infinity otherwise. And then 0 of x is going to be equal to 0 if x equals 0 and infinity otherwise. Okay, and so as a picture, you can sort of think of this as being, here's x, and I'll draw initially, here's I negative. It includes this point, and then immediately, if you sort of write infinity up here, it's going to jump to infinity over here. And this is, okay? And so here is a variational characterization of these functions that's going to be helpful for defining the dual problem. So this notation is going to be a little bit suggestive. I'm going to write this thing as the supremum over all lambda that are bigger than 0 of lambda x, okay? And this one is going to be the supremum of all nu that could be positive, could be negative. If I want to highlight that it could be positive or negative, I'm going to put sort of like a less than, greater than sign of nu x here. Okay, so can anyone argue why this is true? This characterization. No? Were you going to say something?
Just no upper bound.
Yeah, but I mean, can you elaborate on exactly what that means here? Like, say for example, for I naught here, why is this thing equal to infinity if x is non-zero and 0 otherwise?
I mean, so if x is not 0, no matter what, you can always find some value that is a greater value.
Sure, yeah. So in particular, if x is non-zero, you could take nu to be equal to m over x, where m is as big as you want, right? And then you could send it into infinity that way, right? And in the same way, sort of, if x is positive here, I could do the exact same m over x, right, for lambda, and that would give me infinity as I take m to infinity, right? But on the other hand, if x is negative, sort of the best I can do is 0, right? So if I take lambda to be any positive number and this to be a negative number, then that's going to continue being negative. But if I take it to be 0, that sort of satisfies the upper bound, right? And so these are the variational characterizations of these indicator functions. And what's convenient is that allows us to write this optimization problem as sort of like a dual procedure optimization problem, okay? So in particular, what I'm going to do, I'm trying to think if I have enough space for this. Let me do it like this. Okay, so again, this problem, can we all agree that this problem is equivalent? It's like sort of syntactically different, but the exact same as the original generic problem, right? So what I'm going to do is convert this function in terms of these variational characterizations, and again, nothing is going to change, okay? It's going to be the exact same problem. It's still a primal, okay? So if we move, let me try to make this a little more linear. If we look now at the other problem, which is again the exact same, where we minimize over x, but now we're going to first take the supremum over these what are called Lagrange multipliers. If you remember that, these are the Lagrange multipliers. So now I'm going to say take the supremum over lambda, which is now a vector, mind you, lambda, that is component-wise bigger than 0, and a vector nu that is sort of whatever you want. And then I'm going to have the exact same thing we had before, but I'm going to write it in this form. Okay? So now the objective function is f naught of x. plus the sum from I equals 1 to m of lambda I fi of x plus the sum from I equals 1 to p of nu I hi of x. Okay? Does anyone not fully understand that this is the exact same as the original problem? Are we all on board? It's fine if you're not, just let me know. Anyone? Alright, cool. So this, again, the exact same optimization problem as this other one, but what sort of looks nice here is that now we have all these sort of what look like differentiable functions in the top, like all the fi and hi are differentiable. It sort of looks a lot cleaner than this super nonlinear case, right? The only issue now is that we moved this optimization problem into it's this dual step thing that sort of adds another optimization in the opposite direction. It's not like we're minimizing jointly over all these different things that might be easy to do on a computer. Now we're sort of taking the min of this like max characterization and we have this weird game going on, okay? So again, this is currently the primal problem. And now what I'm about to do is you might ask naturally, what if we just switch the order here of the minimum and the maximum? Is that going to change anything? The answer is yes, and the reason is because what happens is if you were jointly minimizing over the same variable, you could result in, that would be the same thing, right? Obviously, if you just flip which thing you're minimizing with respect to. But if you first minimize over x, you could result in like a different function that you're maximizing over instead of the other situation. I guess that wasn't super clear, but we're gonna get to a couple examples where we can explicitly see how, at least for certain values, this isn't the case. Where, for example, we could take this NP-hard problem and turn it into a very easy to solve polynomial problem, for example, by doing this procedure. So again, what I'm going to do here is switch the order in which we optimize this function, and notationally, this thing here is going to be called the Lagrangian of our problem, and it's denoted L of x lambda nu. Okay. And so again, you can minimize over x first now, and then we're going to maximize. So I guess I'll write that as an infimum. And then we're going to take the supremum again over the non-negative lambda, and the nu that are sort of either positive or negative, doesn't matter. Okay? So again, these multipliers are non-negative, but these are whatever you want. And so now this is not the same as the original problem in general. Sometimes it is. And as a result, we're going to call this new problem D star for the dual. Okay? Is everyone on board here? Again, this is like the whole of Lagrange dual theory, right here. That's it. So, does anyone have any intuition on how these two programs are related in terms of, say, the optimal value, D star and P star? All right, well, I wouldn't either. But what the case is that this D star, let me move over this board. So it turns out that the dual problem is always a lower bound to the primal problem. Okay? And that's what's really helpful about having dual programs is, for example, and again, I've said this like 17 times, but we're going to get this in a couple minutes. You can have a primal problem that's extremely hard to optimize in general, but once you pass to the dual problem here, and this is going to pop out in some nice form like this eventually, if you play with it in specific cases, once you pass to the dual problem of this hard primal problem, it turns out that the dual problem could be easy to solve, or could be easier to solve. And so, by passing to that problem, you reduce the complexity of solving your problem, whether it be exactly or approximately. Okay, and so again, that's us talking about generic optimization problems, and now we're almost done here. I'm going to prove why the dual problem is less than the primal problem. It's kind of tautological, but I'll write out the steps, and it's like, okay, I guess that makes sense. And then I'll go through a very simple example and you can see a plot of why the lower bound works in the notes I'll send out. A very simple example of an optimization problem that is non-convex in general, and doing the dual of that, for example. And then we're going to get into some heavier examples in a bit, okay? And so here's the theorem that is like, sort of like the core of all duality theory here. And for this, I'm going to want a little bit more notation. So again, hopefully we're all on the same page about this being Lagrangian here. Sort of you look at this function right here. I'm going to call this first minimization the dual function, okay? So this is going to be called this bit right here, where we just minimize over x first, and then leave nu and lambda as a parameter. This is going to be called the dual function. So that's going to be noted g of lambda nu. Okay, just notation, okay? So here's the theorem, is that for any lambda bigger than 0 and nu, that could be whatever, again, less than 0, bigger than 0, we have g of lambda nu is less than or equal to p star. Okay? And if this is true, does anyone see why the dual problem is going to be less than the primal problem?
Taking the street.
Exactly. So, if you all can buy that this holds, which we'll prove in a second, all we're going to do to find the dual problem is take the supremum over these lambdas and these nus, right? So if pointwise for nu and lambda that sort of satisfy our constraints, they're less than the primal, that means that the supremum over lambda bigger than 0, nu bigger or less than 0 of this function is still going to be less than the primal problem. But this is exactly equal to the dual problem. Okay? Everyone buys that, right? Again, a lot of this is like, it's really not intuitive to just see it, but once you see it, you're like, okay, I guess that makes sense. And so, again, we're going to prove this. So again, this result on its own gives us the upper bound property, the lower bound property we want. So the proof is quite simple. So the proof is that if we take any lambda and nu that are sort of feasible, and we consider a fixed x, okay? So we're going to fix x. So you fix an x, and then for any sort of feasible lambda and nu, then the Lagrangian at a fixed x of lambda nu is going to be at most the supremum of the Lagrangian over all x of these lambda nu. Or sorry, the supremum over all these problems. Sorry. So let me say that again. If you fix an x, the Lagrangian over these certain parameters, lambda nu, is always less than or equal to the supremum over these parameters of the Lagrangian. Sort of by the definition of an upper bound, right? So, or the least upper bound. So this is always less than or equal to the supremum over these two variables of this function, right? So lambda equal to 0, nu is bigger or less than 0. Okay? Is everyone on the same page there? Right? Again, this is just sort of tautological. But now we can just take the infimum of both these sides, right? So what this means exactly is that if we take the infimum, over x on this side, what does that give us?
G.
Yeah, exactly. So by definition, the infimum of L over, for some fixed lambda nu of the Lagrangian over x is going to be g of lambda nu. And on the other hand, if you can recall from the original problem before you flipped the order, which was equivalent to the primal problem, if we take the infimum over overall x of this thing, what do we get?
P star.
Yeah, so it's P star, and the reason is because once we take the supremum, this just gives us our constraints back in the problem, right? That's what we did the first thing. And so what this gives us is that is exactly P star, and again, the inequality is preserved, and so this gives us the theorem 1, okay? Everyone's on board? Again, literally, it's just sort of tautological once you see it. You just run through the steps. So now what we're going to do is use this lower bound property and sort of and just exhibit that it works, basically, for a very small, like 1D problem using the dual, and that's going to help us sort of go through this machinery and practice once before we get to some multidimensional problems. So now here's an example. So we're going to consider the optimization problem that is, again, non-convex in general, but we can sort of look at it and see what the solution is exactly. So this is going to be minimized over some 1D parameter x, x minus 1 squared, subject to the constraint that x squared is bigger than 4. So if you look at this, what this is saying is you have this quadratic that's centered at 1, and all you're allowed to do is be bigger than 2, so you can be over here, or you can be, I think this is, yeah, so this is -2, or you can be over here. And so the point in this set that's closest to the point 1 is what? Anyone? Yeah, just 2, right? Yeah. So, and what does that mean the P star is for this problem? What did you say? No,
I can say.
okay.
Is that 1?
Yeah, it's 1. So, again, you can just look at this problem and see what the solution is, right? But the whole point now is that we're going to show that the dual gives us we're going to look at the dual function and show, and like look at a plot that I won't have exactly, but we're going to have a dual function that's going to sort of like arc below the point 1, and it is going to touch at one point, which means the lower bound is tight. But in general, that's not the case, okay? So, if we look at the Lagrangian here, what that's going to give us exactly, if we look at L, X, lambda, we're going to have the Lagrangian, the x minus 1 squared, the objective function, plus lambda times 4 minus x squared. And then if we expand this, we're going to get 1 minus lambda times x squared minus 2x plus 4 lambda plus 1. Okay? So that's the Lagrangian. It's a function of 2 variables, gives you a real number. Okay? Pretty straightforward. And now, if you find the dual function, I guess I'll just tell you what it is. You can optimize, you can minimize this thing. It's just a quadratic, right? You minimize this thing over x. And if lambda, so again, lambda is non-negative here. If lambda is bigger than 1, this quadratic is sort of downward facing, it's concave, and as a result, the minimum is going to be negative infinity. Okay? But if lambda is between 0 and 1, there is a solution here. Namely, the dual function, g of lambda, is equal to, again, the minimum of this thing over x, which is going to be exactly 4 lambda minus 1 over 1 minus lambda plus 1, which happens to be p star. When lambda sort of satisfies these constraints and in negative infinity otherwise. And note that sort of trivially, when the dual function is negative infinity, that's always less or equal to p star, right? But the interesting part is that for this range of lambda, we know that this function here is less than 1. Okay? That's what the theory just told us. And the way you can sort of see this in the plot is, I guess I'll erase this. Is everyone okay if I erase this, or do you want to? Okay, cool. So, if you look at a plot of this dual function, what you're going to see is if you vary lambda from, say, 0 here to 1 here, what you're going to get is you have like an asymptote that goes down with g. I'm going to write sort of p star equals 1 right here. And it so happens that the maximum of this happens at 1/2, and it touches exactly, and the function looks like this. Okay, so if you want to like look this up, Wolfram, you feel free. But this picture is going to be in the notes. It looks a little bit nicer than this, but this is the gist of it. Okay, is that this function is always bounded above by 1, and we proved this using really complicated techniques, but it's true. And it turns out that this function, when you maximize it, this isn't the dual, right? If you maximize the dual function, that gives you the dual. If you maximize this, it gives you the primal problem exacting. Okay? And so what we just exhibited was a case of what's known as strong duality. Okay? So what we have here is we always know that d star is less than or equal to p star. So that gives us two scenarios. So the one scenario is called strong duality. Strong duality, where d star is equal to p star, namely that the lower bound we just gave is tight. Or what we have is weak duality, where d star is less than p star, which happens very often if the problem is non-convex. Okay? But oftentimes it turns out that strong duality holds, which is sort of what we hope for in many cases. It's just more helpful to have. Strong duality holds very often when the problem is convex. There's like a simple check called Slater's condition that basically tells you if your problem satisfies this with like most of the time holds. Okay. So that was our simple example, and it turns out that, so what we did was we just showed that you could sort of pass to the dual here, and you could maximize the dual problem, solve it, and that would give you, it turns out, the exact primal problem. It turns out that, or you might ask that if you can find the optimal value of the primal problem, that might not be super helpful, right? Because what you actually want is like, say the parameters to your system you're optimizing, not how good the system is going to be, right? And it turns out using what's known as the KKT conditions, the Karush-Kuhn-Tucker conditions, oftentimes you're able to get from your dual solution variables, so in this case lambda, and you can turn those into the x that you have in the optimal case. So there is some, oftentimes that works. Sometimes it doesn't, but oftentimes you can get back. And so there's this whole notion of creating what's known as a dual certificate to your primal problem, where you can optimize your primal problem, right, which gives you sort of a bound that says, oh, well, the minimum of my problem is at most of this, right? Say, because for any feasible point, if you're minimizing a function over some set, any feasible point is going to give you an upper bound to the minimum, right? But on the other hand, you might ask, oh, well, how can we know for sure that your solution to the primal problem is good enough, for example, for our applications? Maybe you're not actually optimal within some certain tolerance. And the answer then is that you can pass to the dual problem, solve the dual problem as well, and that's going to give you some parameters that you can guarantee mathematically just by checking the value of the objective on those problems. You can say that, well, I know the minimum value is between my upper bound for the minimum I just found for the primal problem and the lower bound I found from the dual problem. Okay? Does that make sense? And so between all these things, hopefully you're convinced that this is useful sometimes. But yeah, so let's talk about Slater's condition now. So again, we just talked about what is the Lagrange dual. Now we're going to talk about how you know when strong duality holds, in a pretty short manner. And then we'll go into some examples here. So Slater's condition applies when your problem is what's known as convex, right? So we talked a lot about convex functions, or functions that look like bowls. We also talked about convex sets, namely sets that sort of look like, you might think of it as like a norm ball or something, like a circle in the plane, like a sphere. So what a convex optimization problem is intimately related to that. You're going to be minimizing, it looks very similar to the original setting, minimizing a function subject to some constraints, but in this case the constraints have to result in a domain, a suitable, feasible set that is a convex set, okay? And so there are some sort of scenarios you need to prohibit for that to work, namely the inequality constraints. So the fi less than or equal to 0, I equals 1 up to m, looks the same, but these functions now have to be convex functions. And you could sort of convince yourself that a convex function being less than 0 results in a convex set. If you look at a picture, so here's the point, the level 0, right? The level set of this convex function is going to be this set right here, which is convex. Okay? And so if you sort of intersect a bunch of those inequality constraints, you're going to result in a convex set you're optimizing over. The one other thing you're allowed to have with equality constraints is that they have to be linear, or else if you have this weird nonlinear set, it's going to result in a non-convex. Set, right? For example, if you have like, oh, your point needs to lie on the sphere in Rn, right? You have to have a unit vector as a constraint. Well, if you look at 2 points in that set, if you draw the line between them, that's not in general going to be on the set, okay? And so as a result, the only constraints that are equality that you're allowed are going to be equations of the form ax equals b, okay, for a matrix, A and the vector b. And so this is what's known as a convex optimization problem. So again, here the fi are convex. And then so if that holds in this form, then your optimization problem is what's known as convex. And it turns out that in many scenarios, not all, convex optimization problems are easy to solve. So you can just open your computer and almost exactly in this form type in your optimization problem in MATLAB or Python or whatever you want to do, and it will find you a solution. And if you do it in that way that I just described, it might be a little bit slow, but you're going to be able to do it relatively quickly. And for certain classes of programs that are very general, it turns out, you can solve them very quickly using built-in software in your computer. For example, linear programs fall under this realm because all you have is a linear constraint, and this inequality constraint doesn't exist, and then you have a function f that's just a linear function, c transpose x, right? So again, back to Slater's condition here, is we want to know problems of this form that are convex, when do they satisfy strong duality? And Slater gave a great sort of systematic way to check these constraints and say, oh yes, it satisfies strong duality, or I'm not sure. Okay, so the theorem here that I'm not going to prove, if you want to find a proof, it's in this book in chapter like 5.3.2, I think. And this is online for free available. It's Stephen Boyd and Levin Vandenberg, who works at UCLA, is where Vandenberg is, and Boyd's at Stanford. This book's like the best in the field. So if you want to look at that proof, it's in there. It's like a page long. And it relies on the separated hyperplane theorem we talked about a little bit in class, right? So two convex bodies in Euclidean space can be separated by a plane, basically. So that's like the core part of this proof. So Slater's condition says that if we consider this problem above, and there exists an x in the domain of f naught, and what I mean by this is any point where f naught's not infinity, okay? So maybe you can just incorporate this constraint into the objectives. But basically, any point you might think of it as, where these constraints are all not tight. If that point satisfies your constraint set, then strong duality holds. More specifically, if there exists this x so that fi of x is strictly less than 0 for all I, then strong duality holds. D star equals P star. Okay? Does everyone understand the statement of this theorem? Okay, and so what this is saying on a geometric level is if you look at the constraint set here, it's against a convex body, you might think of it as sort of if you ignore the linear constraint, it's going to look something like that. And what this is asking for is if there exists sort of like an interior point to your convex constraint set. Okay? And if there does, then strong duality holds. It's pretty relaxed. So using this, oftentimes we can just look at a problem and say, well, yeah, constraints are going to be satisfied at some point, or they're not going to be, they're going to be relaxed at some point, and say, okay, well, strong duality holds, I can just solve the dual problem. Okay? So now I'll go into talking about examples of specific dual problems that we can sort of go through the dual. The first one I'm going to talk about is going to be just the regular linear program, and we're going to show that the dual of a linear program, which again satisfies, it satisfies strong duality because of this theorem, because there aren't any fi to check here, and any point that satisfies your linear constraint ax equals b necessarily satisfies Slater's condition, right? And so we can pass to the dual and show that the dual is also a linear program. Which is interesting, right? So the dual of a linear program is also a linear program, and it turns out that the dual of that linear program is the exact same linear program that you started with. Okay, which is kind of interesting. That doesn't happen often. Does anyone have any questions about any of this stuff that I just put forward or anything? No? All right. So again, dual of an LP. So what's a linear program again? Just to write it out, you're going to be minimizing some C star x subject to some constraints ax equals b, where x is positive. There's like about 3 different canonical forms for linear programs, and this is one of them. You might think of this as I have sort of x1, x2 here, and I might be asking myself, okay, well, I guess that's too symmetric. So I have x1, x2 here. I'm constraining myself to be in this non-negative orphan. And I have a subspace that I want to be on for all my points. Namely, this is ax equals b. Okay? Or I guess, okay, think of this as like a projection of like a 3D one, because that would work, but in general, this wouldn't go through the origin, or this would go through the origin, okay? Actually, wait, it wouldn't, right? This works? Yeah, this works, this is fine. If b was 0, it would have to go to the origin, but in general, this is just an affine line. So, again, the picture here is that we have the constraint that we want to be out in this area of the plane, but we also want to be on this subspace right here. And then within that constraint of being basically on this segment, this point to this point, okay? But in this segment, I want to find the point that is most in this direction, okay? Of any of these points. And it turns out if you just look at it, it's going to be this point, okay? But again, this is the picture to have in your mind, okay? Is that kind of thing. So what is the dual of this problem, which by Slater's condition is identical in terms of finding the actual optimal value as solving the primal problem? What we can do is form the Lagrangian. So the Lagrangian of x lambda mu of this problem is going to be equal to what? Can someone tell me what it is? Just write it down for what we've been doing. Anyone? Were you going to say something? I think you said the right thing.
Yeah, follow that.
Which is what in this case?
C transpose x.
Nice, okay. All right. And then what would I do for, say, like this inequality constraint? Anyone? Could be you. All right, well, so we're going to need to convert this to a less than or equal to sign, right, remember? So you can equivalently say that negative x is less than 0, right? But within this, we're going to have the Lagrange multiplier lambda transpose here x, So it's going to be this, the objective, minus lambda transpose x, and then this last bit here, we're going to want to have the new sort of unconstrained parameters, right? And so this is going to be plus new transpose ax minus b, which we want to be equal to 0, right? Okay, everyone on board with this? So from this, we can find the dual function pretty directly. So g of lambda nu is equal to one of two things similar to before. It's negative infinity, otherwise, and I'll write what this is going to be, or it's going to be equal to b transpose nu, negative b transpose nu, if a transpose nu minus lambda plus c equals 0. Can anyone verify that for me? So again, if we minimize this function over x, why is this true? Or maybe start with, why, if this is not true, is it negative infinity? Maybe I'll help by rewriting this initially as a star, let's write this way. I'm going to write this as x star, and then we're going to put a star nu minus lambda plus c minus b star nu. Right? We just rearrange the terms. It turns out to that. Why, if we minimize this function over x, why do we get this thing?
Well, if it's 0, then the x doesn't do anything.
And in that case, what do we get?
Minus b transpose.
Great. And if it is 0, or sorry, if it is not, if this thing is not 0, then what happens?
And you can make x what you want.
Exactly. And so we can just force it. It's basically the projection of x onto a vector, and we can just go in that component and send it to negative 50, right? Whatever. And so this thing is equal to, is the dual function, which means that the dual problem, remember, is just maximizing this function over all non-negative lambda, which only appear in this constraint, right? And whatever nu we want. But I'm going to rewrite this in a little different way here. I'm going to say instead that ax equals negative c plus nu, where nu is some, whatever we want to make this constraint be satisfied, non-negative vector. Okay? And if we look at this element-wise, is everyone on the same board? Me just moving that to the side, right? If we look at this element-wise, what this is saying is I'm maximizing this over nu as long as I can find a lambda that makes this constraint work. And because lambda is anything that's positive, any vector that has positive components, what this is asking, this is equivalent to whenever a star nu is less than or equal to negative, bigger than or equal to negative c. Right? Because if these are equal, then we could just set lambda to be 0 and we'd be able to optimize it, right, over nu. Or if this vector was bigger, we could just subtract things element-wise until it was equal, right? Which is okay. So this is what's known as the slack form of the original program. But again, what we have here is that this is equivalent to dual function is equivalent to a sort of one variable, multivariable entry dual function where A transpose nu is bigger than negative C. Okay? So again, we can just sort of erase lambda. Is everyone comfortable with this so far? Yeah? Okay. So now, when I want to find the dual, what is this? What is the dual problem? Can anyone tell me how to write it out? Or is this something?
Well, we need to maximize it, or?
Yeah. So, I mean, like, well, how would I write this out in the form of like this thing, for example? Or close to that?
Maximize G nu such that X star B is greater than minus C? Or
Yeah, exactly. So if we're maximizing this function, we could never, like, if possible, if it's ever possible to make this constraint satisfied, we would prefer that because we would always want to have this value rather than negative infinity, right? I hope that's clear. And so we can sort of constrain our new parameters, if it's feasible, to only this set. At which point, all we're doing is asking us to maximize this linear functional. Turns out this is also a linear program. It's written as maximize negative b star nu, subject to the constraint that a star nu is bigger than nu c. Okay? And just by keeping it in the slack form we just had, we could have it in exactly this form, but we're not going to do that for now. We're just going to, this is also a linear program, okay? And this is the dual. All right? So again, we started out with this that was better. We started out with this primal problem, and we just did the Lagrangian sort of steps, and we arrived at this dual problem that's also a linear program. And so in practice, what a lot of people do to solve linear programs is sort of do kind of what I suggested earlier, where you sort of do a primal dual algorithm where you simultaneously solve both of these, and they'll both converge simultaneously to the optimal value because strong duality holds. Okay? So now let's look at that other example. I guess, are there any questions about this whole setup? We're just sort of rolling through the steps here again. Hopefully this is like all, I guess a lot of the time this is presented in a way that's like there's like a lot of machinery going on, and hopefully I'm trying to just slow it down so that everything feels a little bit painful. So like, this should feel slow, but at the same time, like, at least when I learned this, it was like way not slow, you know? I don't know. But, now let's look at an interesting problem. So we're going to consider a sort of integer quadratic program, but I'm going to disguise that as a combinatorial program that we're going to look at sort of on its own and write that pretty directly as a sort of weird integerly constrained quadratic program that's going to be hard to solve. And then we're going to take the dual of that program, and it's going to be what's known as a semi-definite program, which you can solve on any computer easily. Okay? And that'll give you the lower bound you want. So again, what's the problem here? Let's say I want to partition. So I'm going to write this down. Let's say I have like a collection of n items, and I want to partition them in a certain way that like maximizes some sort of profit I get. Maybe my name is Amazon, and I'm trying to move certain items into the same area because they're often sold together. But at the same time, by moving, say, all window cleaning equipment to a certain shipping facility, I'm necessarily going to lose money by shipping them back to a different area when someone in a different place wants to purchase them, right? And so, again, just to write this out, what I just said in a naive way, if I have the integers 1 to n, and I want to find a partition of them, then I'm going to sort of identify with the sign of a bit vector, so +1, -1. Let's say I want to partition them between all the I such that xi is equal to 1, and all the I such that xi equals to 1. Okay? And so I'll call this set A plus and this set A minus, but the whole point here is that this partitioning can be sort of determined identifiably by a bit vector x that's in plus or minus 1 to the n. Okay? We're all good on that? And again, let's just say that I have sort of knowledge of a matrix W. So W is going to be in R n by n, or let's call that A actually, so matrix A. And the matrix is going to tell us the information that we need about what it's going to cost for something to be in a certain location away from another product. So if we keep like things that are frequently bought together in different places, it's going to cost us more to ship them, right? And so maybe we want to keep those items in the same place. Initially, I'm going to assume this matrix is general, but at some point I'm going to say if it's positive definite, something will hold, so just keep that in the back of your mind. But yeah, so let's say that I gain a profit Aij when products I and j in the same partition. Okay, and at the same time, I'm going to have a cost negative Aij when ij when they're in different partitions. Okay? So conveniently with the representation I set over there, this is just equal to the total cost or profit of the current configuration I have for these two items is going to be equal to, in total, it's always Aij, Xi, Xj, right? Because if they're in the same partition, that means that the sign of the vectors, that those two components are going to be equal, and as a result, this is going to be 1, and I get the profit. But if they're in different partitions, I'm going to get the cost, negative Aij. And because the signs are going to be different, it's going to result in the negative sign. Okay? And so that's the cost of just this one scenario. And I'll assume that this is symmetric, right? Which gives us the total cost up to the additive constant of like what's in the diagonal here. That gives us the total cost. So if I add up over all ij, so let me just write that out a little cleanly. If I sort of add the total cost, C, of a configuration X, that's going to be equal to the sum over ij. And for good measure, I'm just going to add the cost of like holding an item or something like that. So again, this is I not equal to j. But the cost of holding an item might be like AII for all the diagonal entries, right? And so that's going to be the sum of I equals 1 to n of AII, XI, XI. This is just equal to 1 always, and so I can throw that in. But conveniently, this thing is always equal to X transpose AX. Okay? So it's a quadratic. But it's this right now at least could be whatever quadratic. It could be like super non-convex or something. So again, maybe I'm Amazon and I want to find the configuration of cost vectors here. So which partition of my items is going to be the most cost effective, okay? And so can anyone think of a pretty straightforward way to write this as the optimization problem in the way that we've been thinking about it before? Anyone? Does anyone have an idea? Yeah?
Minimize x transpose ax subject to xi equals plus or minus 1.
Yep. So again, xi equals plus minus 1. Great. So from I equals 1 up to n. I'm going to write this in a different form, but it's going to be the exact same thing. I'm going to say that x squared is equal to 1. Okay? Same thing. So let me flip this page. So I'm going to say that x squared is equal to 1. And this is the primal problem. And this is what's known as a sort of generic, like integer quadratic program. And I'm pretty sure I saw a paper that said that these are MP hard or complete or something to solve. They're difficult in general. Okay, just know that. And you might ask, oh well, this is just a finite set, right? We might be able to optimize. We could just sort of enumerate all the vectors that we consider, right? All these different partitions, and then look at the objective functions for each of these and sort of report that and find the minimum. But how long would that take to do? To enumerate all the bit vectors here? Anyone? Yeah. So there are. If you look at like whether xi is +1 or -1, sort of aggregated for all the bit vectors, that gives you 2 to the n possibilities in the set you're optimizing over, which grows immensely with the dimension. So if this is like n equals 100, you're kind of hosed. But again, what we're going to show is that by passing this MP complete problem, MP hard problem, into the dual, we can find a lower bound that is sometimes very good, that is efficiently solvable, okay, for like n equals like 1,000. And even if we don't have access to like n to the, say, 6th runtime things, if that's still too bad, we can find something that's like n squared, n cubed time, or something like that. Which is, namely, we're going to give us a method for computing lower bounds for this problem that's going to give you something that's tight, but also we can show exactly that the primal problem, P star, this minimization problem, is always bigger than or equal to n times the smallest eigenvalue of a, when a is, I guess, either if it's positive definite or not, but even then, this bound is really only helpful when it's positive definite. So think of a as positive definite now, perhaps, and then we know that the primal problem we can show is bigger than the smallest eigenvalue of a. Okay, and so we'll get that just by the dual. So now the question is how to form the dual of this problem. So what we're going to do is, again, same steps as always. We're going to form the Lagrangian. We only have an equality constraint here, so we have the new. That's going to equal to our objective function, x star ax, plus the sum from I equals 1 to n of nu I xi squared minus 1. Now, I'm going to write this in a slightly different form, this sum here, that's going to be hopefully a little cleaner and easier to work with this matrix equality, or matrix sort of representation here. So again, this is equal to x star ax. But if we look at sort of the sum of nu I xi squared, this is the same thing as looking at x transpose times a diagonal matrix that just has nu as its diagonal, right? So you think about this, it's nu on the diagonal and 0 otherwise, right? It's the same thing as taking x transpose this times x by definition, right? So when you multiply x times a diagonal matrix, you're just going to get nu I xi in each entry, and then when you take the dot product of that again with x, you're going to get nu I xi squared summed. Okay? So this is the same thing as this plus the diagonal term, which I'm going to wrap into here. So it's plus diagonal of nu x minus the sum of the news. So I can write that as a vector of 1's inner product with the news. Okay? Hopefully everyone's good with that. What we have here is a Lagrangian. If we want to solve the dual problem, what we're going to do is minimize this over x first, right? But this matrix here, so again, this is a quadratic form. This is only going to have a finite minimization over x if this matrix here is positive semi-definite, right? Because if any eigenvalue is negative, you could set x to be the negative eigenvalue, and going in that direction is going to give you a negative term here that you could take to infinity, okay, just by moving in that eigenvector direction. So what you end up with is if you minimize over x, you're going to get the dual function g of nu here is equal to, much in the same way that we've already seen, negative infinity if this thing is not positive definite, or if it is, you can, if this is positive semi-definite, that means that every value, by definition, this term is always non-negative, right? And so if we want to minimize it, the minimum is always at least 0. But if we set x to be 0, it achieves that minimum, right? And so if we want to minimize this when this condition is positive definite, that results in just this term. Okay? Everyone buy that? So what you get is negative 1 star nu, which is just the negative sum of the news, the Lagrange multipliers. So this only happens if A plus the diagonal of the news, if this matrix is positive semi-definite, and I'm using that notation, but if that matrix is positive semi-definite, okay? But if I rewrite this as an optimization problem over here in the dual form, what this tells us is that the dual problem is to sort of maximize this, which is the same as minimizing as negative, right? So this is the same as minimizing the sum of the news, 1 star nu, subject to the constraint that A plus the diagonal entries of nu if this matrix is positive semi-definite. Okay? So again, this is the dual. And this is what's known as a semi-definite program. Namely, this thing is convex. If you take two news that satisfy this and you look at their convex combination, what you're going to end up with is another positive semi-definite matrix, right? Because the A is always going to be the same, and taking, it's sort of all you have to do is take the lower bound of the news in that case, and that's always going to be your, as long as you're bigger than that, then you're positive semi-definite. And so this constraint set's convex, right? This is a linear function. It turns out that this semi-definite program, or semi-definite programs in general, are generalizations of linear programs, where instead you're optimizing over a polytope, you're optimizing over, you look at the cone of positive semi-definite matrices. So sort of the S plus to the n is what's denoted usually. If you look at this cone of positive semi-definite matrices, and you intersect that with an affine subspace, sort of like AX equals B here, but you can think of that as like in a matrix version. And then within this constraint, you want to look at like which point is in the most in this direction. Okay? And so it turns out these can be solved, I think, like end of the 6th time or something. It's not super fast, but it is, you can do it for up to like n equals 1,000 without too much difficulty, right? And at the very least, it's much faster than this case. Okay? So this is, again, what we took is this primal problem that's empty complete, and we looked at the dual, and the dual is efficiently solvable along the middle time, and it gives us a lower bound to the primal problem. Okay? And sometimes this dual lower bound is going to be quite tight, and could be very helpful for determining, say, if you have an approximate solution, like you use an approximation algorithm to look at this solution, and you say, oh, well, how good is my approximation in reality, even though your bound might be kind of loose. This allows you to check, and to some degree, how good the bound is. Okay? So, for good measure, what I'm going to do now is sort of use those two things together. I'm going to say that n times the smallest eigenvalue in the positive definite case of A is smaller than the dual problem, which is smaller than the primal problem, which is smaller than the trace of A. So I'm going to prove that inequality, which again, this is like useful insight if we want to look at this original problem that just seemed really hard. This is going to tell us how good our solution's doing. Okay? Can someone pick which side they want to do first? One of them uses the probabilistic method and one of them uses duality. Did you say you want to do the left side? All right, let's do the left side. Well, now I'm kind of hosed because I want to put these on the board. Let me just erase the Lagrange. So what we're going to do is remember that not only do we prove that the dual solution is the lower bound for the primal problem, we also already proved that for any feasible nu, which in this case is literally any vector nu, this is always a lower bound for the primal problem, right? In particular, if we wanted to get some lower bound that was sort of tractable and easy to compute, more so than the n to the sixth, remember, so this is on the order of n to the sixth-ish, I'm pretty sure, something like that, runtime. It's slow, but it's not too slow. Maybe we want to do something that's on the order of like n cubed fast, okay? So what you might do then is pick some specific nu that you can sort of cook up in a way that works, plug that in, and that's going to give you a concrete lower bound. And in particular, what I can do here is take the vector nu to be equal to negative the vector of 1s, but I'm going to scale that so it's lambda min of A times the vector of 1s. Okay? Can anyone see, again, let's just assume right now that A is positive semi-definite. Can anyone see why this is feasible? Why this is not, why this condition holds? If we pick nu to be equal to that vector?
Eigenvalues is the non-unit.
Oh yeah, I guess. That's identity. So yeah, you're right. So what all this does here, by taking this to be the one vector, the diagonal matrix that's constructed from that vector is just the identity matrix. And so by what this does is just shift the matrix A by its smallest eigenvalue, which is going to set one of the eigenvalues to 0, but any of them that are already bigger than the smallest eigenvalue are going to be bigger than 0, right? And so all the eigenvalues are non-negative in this case, and so in the matrices, and this matrix is still symmetric, obviously, and so as a result, this matrix is positive semi-definite, right? And what that tells us is that we can sort of plug it into here and get a lower bound that's useful, and not negative infinity. So again, let's take this, plug it in. What do we end up with? Can someone tell me what the lower bound is? What g of this nu is?
Which is n times lambda.
Yeah. So what we're going to do is look at negative, again this is negative lambda min A times the 1's vector. We're going to plug this into this function, which is the negatives are going to cancel. This is going to come out as a scalar, so we're going to always get a lambda min of A here. And the 1's vector, dot product with the 1's vector is just going to be 1 plus 1 plus 1 n times, so you're just going to get n. So again, this means that the dual function at some feasible point, or at some point, is equal to n times the smallest eigenvalue, which tells us, because the dual problem is maximizing over that dual function, that means that the dual problem, and hence the primal problem, are all bigger than m times the smallest eigenvalue. Okay? Everyone buy that? Again, these are just some machinery that's actually very helpful to have because I doubt that anyone, including myself, could have looked at this problem and determined that in advance. Right? Like, who would have guessed that, right? Like, why would you think that? But now, for the upper bound, this is a totally different technique that does not even involve the dual at all, but it's going to be helpful to see how this sort of sandwiches between each other, okay? In a certain case, namely when the matrix A is close to unispectral, having one eigenvalue, this means that these two problems are very tight. Okay? So, and again, just remember that this is extremely hard to solve and this one's easy to solve, but we're inferring things about this really hard to solve problem just based on the analysis. And this not super heavy machinery. Okay. So, here's what I'm going to show. If we look at our constraint set, let's write this as C, I already used that. S for I'll use K. Okay. The constraint set K is going to be equal to the bit vectors plus or minus 1 to the n. Okay? And what I'm going to do is take a random vector uniformly distributed from K. Okay? I'll read that. X distributed from K. Okay? And what I'm going to show here is that the expected value of X transpose AX is equal to the trace of A. Okay? It's a couple lines out. It's like maybe like 2 or 3 equal signs, right? To get there, but I'm going to show this. And what that means is because the average value of the objective function over its constraint set is the trace, that means there must exist at least one point that's like at most there. Right? Does that intuition make sense for everyone? Again, to repeat, if the average value of a function is something, that means that there must exist some input of the function that sort of is lower than the average value, or at least as close as the average value if there's no variance involved. So how do I show this? Well, the expected value of this is the same as, this is a scalar, right? So this is the same as the expected trace of X transpose AX. But this is the same as the trace of A times X star, because you can cycle things in the trace, right? If you remember from math 30 or 40, whatever, I forgot. That one, you know, the linear algebra. But these are all linear functions, and so you can pull the expectation inside, and this is the same as the trace of A times the expected value of XX star. Does anyone see immediately why this is the identity matrix? Again, if our vector is sort of a random bit vector, why is the outer product, XX transpose, in expectation, the identity matrix?
There's going to be ones all along the main diagonal, no matter what, right?
Yes.
It's going to be either like plus or minus 1 with equal probability anywhere off the main diagonal.
Yeah, exactly. So just to repeat that, if you take a look at the diagonal of XX transpose, that's just going to be xi squared. And because x is plus or minus 1, that's always going to be 1, right? And so the diagonal here is always 1. The off-diagonal entries, because you have sort of xi, xj, where I is not equal to j, those are all like zero mean random vectors, and it's going to be the product of 2 zero mean random vectors that are independent of each other. Is an expectation going to be equal to the product of the expected values of each of those random variables, both of which are 0, okay? And so what we get here is that this is equal to the trace of A, right? So again, to reiterate what we just proved is that the expected value of this optimization problem is the trace. right, over the constraint set. And what that means is that there must exist some x that satisfies these constraints so that x transpose AX is, say, less than or equal to the trace. Right? Because otherwise, if every point was above the trace, that means the expected value can never be that low. So what that gives us is this other side of the inequality, that P star is less than the trace. Okay? So can anyone argue why if A had one eigenvalue, that this means that that strong duality holds here? Yeah?
I mean, isn't it like bound tightly on both sides because n equals 1, and if it has one eigenvalue, then lambda min is just that, and then it's the trace is the sum of the eigenvalues, so you get the same thing on each side.
Wait, what did you say about one eigenvalue?
Oh, I thought you said that if it has one eigenvalue.
Oh yeah, but n is the dimension.
Oh, right, yeah.
But no, but I think what you said is basically right.
Alright.
You're not, I mean, do you want to complete the
I
thought?
think it's because they're still the same thing.
Yeah, exactly.
And you're summing n of the one item.
Yeah, so I mean, if we write this out, what this says is lambda, I'm going to write the eigenvalues of A as like lambda 1 greater than lambda 2 greater than lambda n. Okay? So this is the smallest eigenvalue, all right? So what this says, what we just proved, is that lambda n plus lambda n times, so n times, is at most d star, at most p star, which is at most the trace of A, which is lambda 1 plus lambda n. Okay? But if all the lambdas are equal, these two sides are equal. And as a result, this side is equal to this side, which means that these two things are equal. Which is kind of trivial in a sense, because I think this would just reduce to an identity matrix in that case. If you had a positive definite matrix that's unispectral, I think that I'm pretty sure that's always a multiple of the identity matrix, right? In which case the off diagonal entries are 0, and as a result, any input is going to give you the exact same output, namely the trace. But what this does give you is a sort of tool that can say, not only in the identity case, if you have something that's close to this, you can have a pretty tight duality gap that you're guaranteed, just from this symbol bound, right? Namely, I'm sort of coming up with this on the spot here, but what if we had this situation where lambda I are all less than some value c, and all bigger than some value, I'll call this c, C minus and C plus, okay? So if these two are tight, or close to each other, we would hope that the duality gap is going to be close, but let's see if we can bound that in terms of these things. So this is for all I. So what we're going to have here is that the dual problem, if we look at the left side of this inequality, we're going to have the dual problem. We're going to have the dual problem being bigger than nc minus, whereas the sum of the eigenvalues is always going to be bigger than nc plus. And what this means is if we divide, okay, so if we look at p star minus d star, what's that going to give us? In absolute value, this is at most n times sort of c plus minus c minus. So we can get a concrete bound on the duality gap that's linear in the dimension and sort of linear in the spread of the eigenvalues, okay? So if the diameter of your set of eigenvalues, so again, there's a common notation in functional analysis where sort of sigma of A is going to be the set of all eigenvectors, single values maybe, or eigenvectors, and or the sigma is going to be the set of all eigenvalues of your matrix A. And so what this is saying concretely is that the duality gap here, P star minus D star, is always at most the dimension of your problem times the diameter of the set of eigenvalues of A. Okay? Pretty cool? Again, we have this hard problem, we have an easy problem we can solve, and we can show how close the optimal solution is, right? If we have a special, I mean, you can just look at a matrix and determine this information, and what's nice is that even though finding D star here, so again, this takes like something like probably exponential time 2 to the n. This thing takes on the order of n to the 6th time to solve, right? So you can get this information. And this bound right here, if you want to look at all the eigenvalues, that's going to take something like n cubed time. Okay? So in sort of increasing order of difficulty, we can infer information about the primal problem quite accurately. Okay? So pretty cool. This isn't known exactly as a positive semi-definite relaxation, but oftentimes in this area, what people will do is take NPR problems like the traveling salesman problem, things like that, and they can relax them. They'll write them as a sort of what looks almost like a semi-definite program, but they're going to add some extra constraints, like maybe some entries are integer, just like this case, or maybe you have some other scenario. And so what they're going to do is they write this hard problem as what looks almost like a semi-definite program, and then they relax that problem by, say, loosening or just eliminating the constraints that are hard, like the integer constraints or something like that. And what that gives you is an easier program to solve that always gives you a lower bound that's solved by a semi-definite program. So for example, there's like a 0.8 something something approximation of the max traveling salesman problem that's given from a semi-definite program. I know the person's first name is Michelle, I forgot his last name, who made that like in the 80s or something like that. But things like that are very common in computer science and engineering fields. So again, these tools are very powerful, even though the machinery, if you just walk through it, seems pretty straightforward, right? Hopefully. If it's not, let me know. So those are the main examples of how you take duals and sort of use them to find interesting things. I'm going to have two, maybe one. Do people want to do both these things, or you want to just do one of them and you can call it a shorter day? Shorter day? All right. Would you rather see how to exactly solve quadratic programs, or have me write out the eigenvalues of the largest eigenvalue of a irreducible non-negative matrix as a convex optimization problem? And if you can figure out how to solve that problem quickly, you could probably write a paper about it. Which do you want?
6.
6? Okay.
I have a question.
Yeah.
Is that difference known to be unbounded, D star minus D star? Is there examples where it gets arbitrarily large? I know that bound is unbounded, but
So it's so what you're saying is
can that error be arbitrarily bad, right? Or, can it,
yeah. In this specific problem,
or in general?
in general, I'm pretty sure that it can be arbitrarily bad.
Okay.
I'm pretty sure. Again, I don't have an example on the top of my head right here, but what you're going to want to look for, if you want to find an example of this, is A, just look at this book, it probably has it somewhere. B, what I would look at is try to construct a non-convex program that has some weird constraints that you can still probably solve exactly here. Like maybe you could take the dual of the eigenvalue optimization problem, not the one I'm about to say, but like the regular way you look at eigenvalues, like as a min-max, right, over that thing. That problem is non-convex, but we can solve it efficiently, right? And so what you could do is check, oh, well, here's the optimal value, and then I can look at the dual, and likely I would guess that there's some duality gap there, possibly, at which point you could just solve the dual, which might be convex, right? And just check if those are equal. And then maybe fill out the dimension of the infinity or something like
I
that.
see.
If you wanted to look at this problem, you might consider the case where you have like one, maybe you have a matrix that's easy to deal with that would make the semidefinite program really easy to solve, but you could get a tight amount on the dual. I'm not sure exactly. Again, I don't really know, but what I would probably do is take A to be something like 1, 1, 1, 1, 1. So these are, it's going to be like an arrow, right? So you're going to have 1 and then 1 down here. I don't know if that's, does that have a weird spectrum? I'm not sure. But maybe we can take something like this that has like really lopsided eigenvalues, and that would make this bound apply.
Yeah.
That's what I would guess. Like maybe you have a matrix that has like all ones here, and then, oh, actually, what you might be able to do is look at the matrix that's diagonal. So you take like n and then 1, 1, 1, 1, 1 here. The optimization problem you have, the solution is always going to be the trace of this. Okay, so P star is always going to be equal to the trace of A, which is going to be equal to n plus 1 times n minus 1, so n minus 1, which is always equal to 2 n minus 1. And perhaps you could just solve the dual problem with this, and because it's super easy to invert, I'm sure that'd be very easy to do in maybe closed form. You might be able to look at that and it might not be tight. But I'm not going to guarantee anything, okay? But that might give you an example of this. But again, check out the book, it's probably not. I don't know if it's on my head. Do you have any other questions? All right. So this is a formula. Or maybe I'll write out the eigenvalue formula of a regular arbitrary matrix. You all might have seen this, okay? So if you have a generic matrix, well, let's call it a symmetric matrix A, and we look at the problem, maximize x transpose AX, subject to the constraint that the norm of x equals 1. What is the solution to that optimization problem? Has anyone seen this before? Yeah, so it's the largest eigenvalue. So that's just going to be lambda max of A. Again, symmetric matrix, okay? It turns out that, again, this is for an arbitrary symmetric matrix. There's a lot of scenarios where we don't necessarily have a symmetric matrix, but we do have a matrix with non-negative entries. For example, when we're computing the PageRank algorithm, right? What you do is you have this non-negative like Markov matrix, so you sort of iterate a vector on it to try to compute the like PageRank vector, which is basically corresponding to the largest eigenvalue and largest eigenvector. And the Perron-Frobenius theorem tells you that there is, for any non-negative entry matrix, there is a maximal eigenvalue that is positive. Again, this is, let's just assume right now that all of the entries of the matrix are positive, okay? So there's a positive eigenvalue that's unique. All the other eigenvalues have imaginary part or something like that, but there's a real positive eigenvalue. It turns out that there's a principle called the Collatz-Wayland, I think that's how you pronounce it, principle. And I think this is the same Collatz that the Collatz conjecture. So there's this thing called the Collatz-Wayland formula. Which is for the specific case that you have a matrix A and R, like n by n, with the entries ij that are, let's just say positive for now, And the matrix A is what's known as irreducible. So and what this means is, for example, if you draw a random matrix and take the absolute value of the entries, that's going to be irreducible almost surely. But what this means is that if you look at the graph corresponding to this matrix, which in this case, I guess this would always be irreducible, I'm pretty sure. But yeah, so I guess you don't even need that for the positive case. But in general, if you have a matrix A, let's say this is going to be 1, 1, 0, 0, and then like 1, 0, 0, 0, 1, 1, 1, 1. This matrix is not irreducible. Why? If you look at the corresponding graph, so let's say what this corresponds to is a directed graph, where you look at, you have like 4 vertices, 1, 2, 3, and 4, and vertex 1 here has an edge between 1 to 1 and 1 to 2, okay? So 1 to 1, 1 to 2. Vertex 2 has an edge back to 1. Vertex 3 has an edge to itself and to 4, and then 4 sort of does the same thing. If this corresponding graph has sort of non-connected components, but in the directed sense, namely if you have one vertex that you cannot get to another vertex, right? If you can start at a vertex and there exists no path to another vertex, that's what's known as irreducible. So the Collatz-Wayland formula says that if you have a non-negative matrix that's irreducible, or also you can just take a matrix with all positive entries, that's also fine, and ignore the irreducible part, then the largest eigenvalue of that, which is known as the Perron eigenvalue, which corresponds to, say, like the Google PageRank algorithm, that eigenvalue you're looking for, the largest eigenvalue of that is equal to a simpler optimization problem. You're going to minimize over positive vectors x, or non-negative vectors, after you maximize from 1 less than or equal to I, less than or equal to n, of ax I over xi. So that's true. Does anyone see why this might be a thing that makes sense? So if x was an eigenvector corresponding to lambda, for example, then ax is going to be equal to lambda x. And so lambda gets pulled out, and what you have is xi over x, which is 1, and that goes to the same thing, right? But the whole point here is that you minimize this in a certain order, you're going to get the biggest eigenvalue. Okay? And it turns out that the x you get from this is also the biggest eigenvector. But what's nice is that what you can do is transform this constraint into an unconstrained problem just by saying if you restrict this to be positive vectors, you can sort of let me do this over here. If this vector x is positive, you can take the logarithm of the entries, right? And so what you can do is set z equal to zi is a vector with entries log I. And if you do this, the problem naturally transforms itself if you take the log of the problem, because the logarithm is monotone, you can sort of bring it in through here, that's fine. What you get is that the log Perron eigenvalue is equal to a minimization over z of the max from 1 less than or equal to I less than or equal to n of log sum I equals 1 to n of e to the zi plus log a ij, I guess I'll put j here, sorry, minus zi. So again, all you have to do to transform this is you take the log of this and then use this substitution. And it turns out that the Perron eigenvector, or eigenvalue, and the corresponding, what you can do is if you solve this, you just have to exponentiate the entries to get the Perron eigenvectors. What this gives you is an optimization problem. And you might ask, oh, well, this optimization problem, if you look at it, is non-convex, and you would assume, therefore, hard to solve, although it turns out you can get eigenvalue algorithms that are pretty fast. This is a convex optimization problem that is not clear if you can solve this faster than, say, the power method, which is usually used to compute these sort of eigenvalues. Okay? So I guess the problem that you might think about is this form is a convex optimization problem that will give you the same solution that the power method will give you, but it might be able to do it faster, and it might be able to do it in a way that doesn't depend on, say, the spectral gap of your matrix, namely the eigenvalue number 1 over the eigenvalue number 2, gives you the convergence rate of the power method when you're computing eigenvalues. Have you heard of that before? And so if you could find a way to use this formulation that's convex, you would just maybe need to play around with convergence rates in a certain way, and hopefully that might work out. Or maybe you look at the dual and show that the dual is easy to solve, and because this is unconstrained, there's a strong duality here, so that would give you the corresponding solution. This would be an interesting development. So as far as I know, I don't think anyone's used convex optimization to find Perron eigenvalues before, but this is how you might go about it. Okay. So yeah, I guess that's the whole problem. The reason this is a convex problem, I guess I'll conclude with that. It turns out this is called a log sum. And if you sort of think of this as one variable, you just shift it around, right? That doesn't change convexity at all. This is what's called a log sum x function, very original. And it's convex, it turns out. It's in a purple book if you are interested. And this is an affine function. Okay, it's just you're adding a negative linear function. As a result, this inner term here is convex. And it turns out that the maximum of a collection, a family of convex functionals, is jointly convex. Okay? So sort of if you look at a picture here, I have this quadratic or exponential, something like that. I take a line here, and I take a line here. These are all convex. But if I look at the maximum here, it's going to be this thing. That function, right? I don't know, minus the squiggles, but you know what I mean. This thing is convex. And so as a result, if we look at this function, called the f of z, this function is convex, and this corresponds to an unconstrained convex optimization problem. Although, and the catch is, that this may be, at least at n, or something like n, or maybe like some subspaces that are small points, non-differentiable. So you might be a little bit worried about that, right? If you could run, say, Newton's method on this thing, an efficient way that relied on the structure of your matrix A, this could be interesting, and possibly a lot faster than the power method, who has linear convergence, right? Because Newton's method has quadratic convergence. But if you were to use the conventional methods for dealing with non-differentiable convex optimization problems, like, for example, doing compressed sensing, those tend to not have strong convergence rates, at least in theory. So you might need to do something that's a little bit more special than that, right? Anyone have any questions about anything? I think we're mostly done. You ready to say something? All right. Cool. All right.
Yeah, no problem.
I think you can do that.
So the first day you can begin